Hello guys, welcome back to my channel, and in this important video we are going to actually cover some important representations of the gamma function, and after doing that we're going to use all those results to get a representation for the digamma function. So let's get started with our proofs. Okay, so first we have the Gauss representation of the gamma function. So for doing that, let's define an integral. Let's call it I. Define it as integral from 0 to infinity of e to the negative x times x to the z minus 1 power dx. And this might seem familiar. This is just the gamma of z. And this is what we call Euler's definition of gamma. Euler's integral definition of the gamma function. And we're going to actually work with this. So first, before starting our proof, you should know this fact that E can be defined as limit as n goes to infinity of 1 plus 1 over n raised to the nth power. That's E. But if we want to generalize this into a function, say e to the x, we can write this as limit as n goes to infinity of 1 plus x over n to the n. So we take the x in place of 1 inside, and similar thing for e to the negative x, we can write that as limit as n goes to infinity of 1 minus x over n to entire thing to the nth power. So I'm going to actually use this definition for e, plug that in here. So we have I is defined as integral from 0 to infinity of limit as n goes to infinity of 1 minus x over n to the nth power times x to the z minus 1 dx, and this still is equal to the gamma of z. Now what I'm going to do is I'm going to actually take the limit outside. So limit as n goes to infinity, but wherever we had infinities in two cases, in this limit for n and also for this integral. So wherever we had infinities, I'm going to write n, because anyways we are having a limit as n goes to infinity. And then this can be written as 1 minus x over n to the n times x to the z minus 1 dx. That is the gamma of z. Now what I'm going to do is I'm going to generalize I. So let's call it I sub n, and we're going to define that without the limit. So integral from 0 to n 1 minus x over n entire thing to the nth power times x to the z minus 1 dx. But this is not equal to the gamma function because we don't have the limit now. Think of n as a free variable, another free variable like z of the gamma argument. Because since we are not taking the limit, this can't be set equal to the gamma function. But notice one thing, so if we take the limit as n goes to infinity of I sub n, that is equal to this I that we originally had, and that itself is equal to the gamma of z. So only when we apply the limit on this I sub n, that's when we obtain a gamma. So what we are going to do is we're going to do simplification on this. So let's try to see if we can do some simplification of I sub n, and then we'll take the finally at the end we'll take the limit as n goes to infinity. It may seem at start that it is not going to work, but trust me, it will. So like I just said, we actually need to play with I sub n, and we know this relation. So after say simplifying this, we'll just apply the limit as n goes to infinity and we'll get some result, hopefully. So what we are going to do is we are going to, this is like a weird expression, 1 minus x over n to the nth power. It's really weird. and it will be great if eventually we can get rid of it. So what I'm going to do is I'm going to be differentiating this and I'm going to be integrating this in a process that's called integration by parts. So integration by parts works like this. So if you have integral of some function that you want to differentiate, say d times some function that you are eventually going to integrate, dx for example, then it's going to be the antiderivative of I times d minus integral of derivative of d times antiderivative of I of x, and all this is integrated with respect to x. So this is the formula we're going to use. I hope you know this formula by now. So I sub n will be, well, we need to integrate this. So this on integration will be x to the z divided by z. Then this term as it is 1 minus x over n to the n, evaluated from 0 to n because it's a definite integral, minus integral from 0 to n of x to the z over z just remains the same, and we have derivative of this is 1 minus x over n to the n minus 1, but we still need to multiply by the original power but divide by this n because that's the coefficient of x by the chain rule, and also by this negative. So negative negative will be a positive n like this dx, and I won't cancel these n's out because they'll help us to actually find a pattern. So when you plug in n in place of x, we have 1 minus n over n. N over n is 1. Since we don't even have a limit, n is like a free variable, we don't even need to bother about lingering infinities or divergences. So 1 minus 1 is 0. 0 to some finite power is 0, making this entire term go to 0 at n. And when you plug in 0 over here, this x, this inner term will just be 1 to the n, but this x will make the entire expression multiply by 0. So even at 0 you have 0. So entirely this expression goes to 0. So we're just left with n over n times this z times integral from 0 to n of x to the z times 1 minus x over n times n minus 1 dx. And let's again go for integration by parts. Again differentiating this and integrating this. So now we are left with n over nz divided by the new coefficient of z after anti-differentiation is z plus 1, and we have x to the z plus 1 times 1 minus x over n to the n minus 1 power evaluated from 0 to n minus integral from 0 to n of, bring the old power down, so we have n minus 1 out like this, divided by this a negative 1 over n, negative negative will be a plus, and we have x to the z plus 1 because we anti-differentiated it, and 1 minus x over n to the n minus 2 because we are differentiating this dx. So now again if you plug in n in this expression, this will go to 0, and even for 0 because of this external x to the z plus 1 it will go to 0, making this entire term go to 0. So all we are left with is n times this n minus 1 factor divided by nz times this n times this z plus 1 that we had, and integral from 0 to n of x to the z plus 1 times 1 minus x over n to the n minus 2 dx. That is indeed your I sub n expression. So since we are keeping on to do this integration by parts procedure again and again. We will be again and again, doing this integration by parts procedure, because as I said at the start, we need to get rid of this weird exponential term that we had over here. So we need to get rid of it. So that's why we chose to differentiate it, because its power was going down. So eventually we want its power to go down to 0, because anything to a 0 power is 1. So we'll be getting rid of it with power 0 if we keep on doing this integration by parts until the power of this 1 minus x over n expression becomes 0. So if we choose to do that, say another n minus 2 times, we'll be adding um, n minus 2 here, because that's what happening, right? If you subtract 1, you're adding 1 on the x to the z part. If you're subtracting 1 again, or subtracting 2 from the original expression, you're adding 2 to the x to the z minus 1. So, and you're developing this pattern of factors, which is pretty evident, I think, because this n minus 1 is always 1 greater than what the power of this 1 minus x to the n term was. So if we reduce that to 0, this power to 0, we will end up with an eventual factor of 1. So with n times n minus 1, that will go on till 0. So n times n minus 1 times n minus 2 times n minus 3 till 0 till 1, because that's when, for the last expression, this will have a power of 0. And notice the denominator with nz times z plus 1, and this final factor was matching whatever power x had. So in our case, since we are subtracting n minus 2 here, we'll be adding n minus 2 in here like this. So eventually this pattern of n times z times n times another linear expression in z will go on until n times then this power of x, right? Because this was the power of x, z plus 1 plus n minus 2, and this reduced down to 0, because that's what was the plan told us to do, and that is 1 on the reduction. So we have this developed pattern now. So n times n minus 1, that goes on till 1, divided by with n times z plus 1 times n times z plus 2, or you can say goes on till n times z n plus z minus 1. I'm just simplifying this, and we have integral from 0 to n of x to the z plus n minus 1. So again, this and this is matching like the original pattern said. So now integrating this is easy. We just have to use the power rule. So we have n times n minus 1 going on till 1, divided by n times z plus 1 going on till n times n plus z minus 1. And when you integrate this, you have x to the z plus n divided by z plus n evaluated from 0 to n. And before evaluating this, I would just like you to tell me how many terms of n there are. So it's being n is being multiplied with itself how many times. So if you notice, for every linear z term there was an n term, until this term. This came afterwards. So how many of these z terms are there? So let's check. Last term minus first term, which is a z, will give us n minus 1 plus 1. That's how many the number of terms are there. So there are n terms. by this. So there are n is being multiplied with itself n times. So we have n times n minus 1 till 1, and in the denominator we have n to the nth power times z plus 1 going on till n plus z minus 1 and n plus z, this last term. And when we plug in n, we have n to the z plus n like this, and for 0 everything goes to 0, so don't bother. That's I sub n basically. I sub n is basically n times n minus 1 going till 1 over n to the n times z plus 1 going till n plus z. I'm just ignoring this second last term. And we can write this as n to the z times n to the n. So the great part is these crazy terms cancel out. All we are left with now is take the n to the z in front, n to the z over z like in the front like this, and write the remaining terms. So n times n minus 1 going till 1 divided by z plus 1 going till n plus z. That's basically what your I sub n evaluates to. And now this, believe me, this is the most simplification we can do for I sub n, except we can probably generalize using a product notation. So n to the z over z, and we have a product from say k equals 1 to n. This is just a product index. So we have k, because if you check, we'll have for k equals 1 we'll have 1, then 2, 1 times 2 times 3 till n. So we are having that kind of relationship here, divided by z plus k, because for k equals 1 we had z plus 1, then z plus 2 till z plus n. So this is a valid representation of our simplified expression. Now we have simplified I sub n to the the greatest level that we could. So now it's actually time to apply the limit as n goes to infinity of I sub n, which is nothing but I, which is nothing but gamma of z. So if we do that, we have limit as n goes to infinity of n to the z over z, and the product from n equals 1, k equals 1 to n of k over z plus k. And although at first this may look like this is diverging to infinity, because if you take the limit over here, it's like infinity to the zth power, which is like exponential infinity. It ideally should be diverging big time, but it's not. It actually converges to gamma of z. So limit as n goes to infinity of n to the z over z, and product from k equals 1 to n k over z plus k. And this is what we call Gauss representation of gamma. Yeah, it's a pretty neat expression. It's useful in most cases, and it's one of the places where we're actually using the product notation. Last time we used the product was for the infinite product representation of the sign. So this is one useful relation. You can also call this the functional equation of the gamma function. Whatever floats your boat, but this is what we proved through the entire process. So now if we want to prove the Weierstrass representation of the gamma function, it's actually pretty sequential. So what we do is we use the functional equation of the gamma function that I just proved on the previous page. And what you do is you tweak it slightly. So what you do is you write this as limit as n goes to infinity of e to the natural log of this original thing, whatever we had, n to the z power divided by z times product from k equals 1 to n of k over z plus k. Because since natural logs and exponentials of base e are inverse functions of each other, they will eventually cancel out to give us n to the z. So it's actually a property that any quantity a can be represented as e raised to the natural log of that quantity a. It's a pretty standard result, one of the most basic properties. So I did that, and there is another property for natural log. So if you have natural log of p to the power q, this can be represented as q times natural log of p. So I'm going to do that on the top here. So we have limit as n goes to infinity of e to the z times natural log of n over z times product from k equals 1 to n of k over z plus k. Fair enough? Nothing unusual until now, I expect. So now I'm going to distribute this limit over the product, and we can totally do that. It's a valid property of limits. A limit as n goes to infinity of e to the z times natural log of n over z, and on this side we have infinite product from k equals 1 to infinity of k over z plus k. So I split this limit on this first term and then this infinite product term, rather just this product term, which after applying the limit separately over the product, this became an infinite product. So fair enough. So notice the first term that we have here. We have natural log of n as n goes to infinity. Doesn't it seem kind of familiar? I mean, what's the last quantity that you learned that had such kind of behavior? Limit as n goes to infinity of natural log of n. So recall that the Euler Mascheroni constant was defined as limit as n goes to infinity of the harmonic series of nth harmonic number minus natural log of n. So notice that we had limit as n goes to infinity of natural log of n over here. So notice we have this part here as well. So we have a natural log of n as n goes to infinity over here in the exponential, and also in this definition of the Euler Mascheroni constant. So what I'm going to do is we can define a negative Euler Mascheroni constant to be limit as n goes to infinity of natural log of n minus nth harmonic number. I can do that, I can totally do that. But this is not alone, right? This natural log of n is not alone, there is a z associated with it. So don't worry, let's just multiply both sides by z. So in order to get a negative Euler Mascheroni constant, we need to subtract by this nth harmonic number in the same limit. So what I'm going to do is I'm going to write limit as n goes to infinity of e to the z times natural log of n minus z times nth harmonic number, but we just can't subtract it like this. It will change the entire meaning of the expression. So we just add it again. So it's like adding a zero. That we don't mind doing that. And we have product from k equals 1 to infinity of k over z plus k as it is. So notice, factoring out the z, we have natural log of n minus nth harmonic number in the limit as n goes to infinity. So on top we just have limit as n goes to infinity of e to the negative z times Euler-Mascheroni constant plus z, this was unchanged, plus z times nth harmonic number over z times the product from k equals 1 to infinity of k over z plus k. So notice that e to the negative Euler-Mascheroni constant times z no longer depends on this limit n. So we can just take it out. We have e to the negative Euler-Mascheroni constant times z over z, and we can split this. We can write a sum of arguments in an exponential as product of two different exponentials. So limit as n goes to infinity of e to the z times nth harmonic number and product from k equals 1 to infinity of k over z plus k. But what is the nth harmonic number? That's the sum from k equals 1 to n. Let's have another indexing variable m, 1 over m. So that was the nth harmonic number. If we do make that substitution, we have e to the negative Euler-Mascheroni constant times z over z, limit as n goes to infinity of basically e to the z times, and in the exponential argument itself we have sum from m equals 1 to n actually of 1 over m times product from k equals 1 to infinity of k over z plus k. But if you have say sum in an exponential argument, so say if you have e to the x plus y, this can be written as e to the x times e to the y. So similarly, if you want to generalize, if you have e to the sum of from I equals 1 to some weird infinity of say a sub I, that can be expressed as product from I equals 1 to infinity of e to the a sub I. So that I'm going to use just this property now. So if e to the negative Euler-Mascheroni z over z, limit as n goes to infinity of the product from m equals 1 to n still of e to the z over m like this, and the product from k equals 1 to infinity of k over z plus k. So what we can do is we can change this m to a k, it doesn't matter what indexing variable we have, and then a product of two infinite sums can be written together. So e to the negative Euler-Mascheroni over times z over z, this can be written as sum from k equals 1 to infinity of e to the z over k times sum from k equals 1 to infinity of k over z plus k. So all I've done is I'm just applying this limit over here. So this n changes to infinity, and a product of two different products is can be taken inside together. So we have e to the minus Euler-Mascheroni constant times z over z, and having a common product from k equals 1 to infinity of e to the z over k times k over z plus k like this. Now we can actually flip this around with e to the minus small gamma times z over z, product from k equals 1 to infinity of e to the z over k, and split this up with z plus k over k inverse because reciprocal, because we just took the reciprocal. A reciprocal of the reciprocal is just the normal expression itself. So we can still have a final simplification, e to the minus z over z, and then product from k equals 1 to infinity of e to the z over k, and then this will become 1 plus z over k to the minus 1 power. And what is all this equal to? Gamma of z, right? So there we go. Here is the most popular product formula for the gamma function. But if you want, you can simplify this further. Notice if you multiply both sides by z, you'll have z times gamma of z, which by the recurrence relation of gamma is just gamma of z plus 1. So gamma of z plus 1 is basically e to the negative Euler Mascheroni times z, and product from k equals 1 to infinity of e to the z over k and 1 plus z over k to the negative 1 power. And this is what is famously known as the Weierstrass representation of the gamma function. And this is actually more popular than the functional equation or the Gauss representation of the gamma. It's more popular than this that we started with. So it's actually a neat result to actually know. And it is going to, believe me, it's going to help us figure out a lot of stuff. It's going to help us figure out the proof for the reflection formula for the gamma function and many other things. So like I just said, this Weierstrass representation of the gamma is extremely useful, and it's not only useful for proving the reflection formula of the gamma function, but it's also useful for deriving a formula for the digamma function. So we know the digamma of z is basically the derivative of the natural log of gamma. So that is basically gamma prime of z over gamma of z. And if you change z to z plus 1, you'll have gamma digamma of z plus 1 is equal to gamma prime of z plus 1 divided by just a gamma of z plus 1. So since we have a gamma of z plus 1, we can actually derive an expression for digamma of z plus 1. How, if you ask? First you take a natural log, as I said, and then after taking the natural log, then you differentiate both sides. So if you have natural log of gamma of z plus 1 is natural log of this entire big expression. So it's natural log of this entire product e to the minus Euler Mascheroni times z times product of from k equals 1 to infinity e to the z over k times 1 plus z over k negative 1 power. Fine, but we know that the natural log of any product can be decomposed as a natural log of separate sums. So if we do that here, we basically have natural log of gamma of z plus 1 is equal to natural log of e to the minus Euler Mascheroni times z plus, because of this property, natural log of product from k equals 1 to infinity of e to the z over k times 1 plus z over k to the negative 1 power. So we have minus Euler Mascheroni times z plus natural log of a product can, this expression, this property actually can be generalized. If you have natural log of some product, this can be expressed as a sum of natural log of whatever quantity we had. So this is basically sum from k equals 1 to infinity of natural log of e to the z over k plus natural log of 1 plus z over k to the negative 1 power. So we have minus Euler Mascheroni times z plus sum from k equals 1 to infinity of, now we are just left with a z over k outside, and we can bring the power down by this property. So we have minus natural log of 1 plus z over k, like this, and that is just the natural log of gamma of z plus 1. But now let's take the derivative with respect to z on both sides. So when I do that, we have minus Euler-Mascheroni plus sum from k equals 1 to infinity of 1 over k minus 1 plus z over k and 1 over k on top by the chain rule basically. This is basically gamma prime of z plus 1 over gamma of z plus 1, which by definition is a digamma of z plus 1, and it's equal to minus Euler-Mascheroni plus sum from k equals 1 to infinity of 1 over k minus, taking the LCM, we'll have k plus z over k, and this k will cancel the denominator, so we'll have 1 over k plus z, like this. And that's actually a formula for the digamma of z plus 1. And that's exactly what I had used in my very first introduction to gamma digamma video. And many of you at that point were wondering where this formula came from. Well, this is where the formula comes from. And if you want to actually write an expression for digamma of just z, then for all z's you change them to z minus 1s. So we have sum from k equals 1 to infinity of 1 over k minus 1 over k plus z minus 1. But I'm saying start the sum now from k equals 0 to infinity. So reducing one initial value will make us add 1 to all the k's that were there. We'll have k plus 1 plus z minus 1, like this. So the digamma of z is minus Euler-Mascheroni plus sum from k equals 0 to infinity of 1 over k plus 1 minus 1's will cancel out, 1 over k plus z. And now if you want to find the value of the digamma of 1, again you plug that in, you have minus Euler-Mascheroni plus sum from k equals 0 to infinity of 1 over k plus 1 minus 1 over k plus 1, plugging in basically 1 in place of the z. These will cancel out, giving us digamma of 1 is just negative Euler-Mascheroni constant. So that's another way of proving that the digamma of 1 is the minus Euler-Mascheroni constant. So I think that's it for this video. It was a hell lot of proofs and many things that were revealed to us through the process. So hey guys, please like, share and subscribe to my channel. Recommend me to your friends. I want more subscribers and more views on my videos. And in the meantime, stay home, stay safe, keep on doing math. Have a great day and peace out.